Chapter 18, Electric Potential. In the previous chapter, we discussed electric forces and electric fields. Now we're going to talk about electric potential and electric potential energy. Obviously, electric force can move charge from one place to another place, and force times displacement is equal work. If you remember work and energy theory, work is related to change in energy, and electrical work specifically is related to electric potential energy. Electric force is related to electric field through this equation. Force is equal charge multiplied by electric field. Assume the charge will move a distance delta x. So work done by electric force on the charge is then obviously F times delta x. The electric force is conservative, the same as gravitational force, force of gravity. So the work done is independent of the path. That means we're only interested in initial point and the final point, and it doesn't matter if from this point to this point charged move this way, that way, or this way. We're only looking at initial position and final position. If the electric force does amount of work W on a charged particle, there is an accompanying change in electric potential energy. For potential energy, we're going to use symbols potential energy, electric, or sometimes you're going to see PE, electric. This is similar to what we used before for, if you remember, we had potential energy, gravitational, we had also elastic potential energy. Now we're adding to the list electric potential energy. Let's look at this diagram over here. We're given positive charge that is placed in an electric field, and because the charge is positive, an electric field goes this direction, it's going to experience electric force according to this formula, and electric force is going to be directed this way. And assume we're moving charge from point A to point B with the distance traveled delta x. So now let's apply our formulas. Change in potential energy is equal negative work done. Negative work is negative force times displacement. We know displacement from here. Force we know from here. So we have negative QE times delta x. I would like to emphasize here that change in potential energy, delta PE, electric, is actually negative here. Let's compare what would happen if I have a ball dropped down to the earth. Right? So initial position is right here on top with height h, and final position, height is equal 0. So change in potential energy is equal final potential energy minus initial potential energy is equal 0, because height is 0 over here, minus initial potential energy, mgh, so it's equal minus mgh. So it is also negative sign, the same as we had in our example. Change in potential energy is negative in both cases because object or charge are moving in the direction of force. So there's force and there is our displacement, same direction. In the next example, we have still positive charge, but we're moving from point B to point A, opposite direction. Electric force is directed this way, right? That's over here. But we're moving from B to A, That means we have to apply force that goes against electric force. This situation is similar to when we have a ball, apple object on the ground and we're moving it up. So in this example, force going to have different sign, and but change in potential energy is going to be positive, exactly like what happened if we're moving an apple or ball from Earth to the height h. Let's just see how it happens here. Delta potential energy is equal, final potential energy is mgh minus initial potential energy is 0, so it is positive mgh. This was gravitational. In electric potential energy, it's going to be also positive, just like here, positive sign, because we're moving against electric force. We can also understand it in this way, that the positive amount of energy can be stored in a system that is composed of the charge and electric field. So I'm moving a charge against field lines and the charge getting more and more potential energy. But then change potential energy is positive. So it's like also if you think about elastic potential energy, how that works for elastic energy. So if you think about elastic energy, we have given a spring. If we compress it, right, it gets more energy. It becomes compressed, so it gets tight, and it stores energy in it. The same as with electric potential energy, we can store energy if we move charge against electric field lines. And the stored energy, obviously, just go back to our original slide, can be taken out of the system now, the same as with a spring or with a ball. The ball falls down. So if we let charge go after we place it in position A, we let it go and it moving to position B, so it releases its energy, and change in potential energy now is negative. That means this energy went somewhere. Sometimes it can shows as an increase in kinetic energy of the particle, so it just moves faster. Let's look now at a different situation. Potential energy of a system of 2-point charges. Unlike before, when we were just given electric field lines and it was set up somehow mysteriously, we didn't think about it. Now we're just given charge 1 and charge 2 at a certain distance, initial distance Ri. We're going to move one charge toward each other, namely second charge toward charge 1, and the final distance between those two charges is going to be our final. Obviously, if those are like charges, they will repel, so we have to overcome the force, and if they are unlike charges, they will attract. If we would think about it like in terms of force of gravity, in the first situation, because they repel, we're moving object up away from Earth, and attract, object falls down towards the Earth. We can represent equation for force, electric force. It's Coulomb's law, K Q1 times Q2 multiplied by R squared. We can express it as a plot over here. So if we given like charges, similar signs, the force is positive, and it's going to go, it falls down as R squared because of this dependence, and try to plot it. If the charges are unlike, then the sign of this force is different. It's negative, obviously. Just plug in negative and positive over here, you'll get negative value. What's happening with potential energy? Potential energy of the system of two charges is going to be given by this expression, K Q1 times Q2 divided by R. not by r squared as we had before. How I can get this formula? To actually calculate this formula, you need to do integration, and this is beyond our course. So you kind of have to believe me that what it is, or I can hand wave and explain it to you in a kind of lousy way. So if there is a work is equal force times displacement, it's equal change in potential energy. So kind of if force is given by k q1 q2 over r squared, displacement is kind of r, so it's not quite r, so r squared cancelled out here, so you would have expression for potential energy q1 q2 r. So this is in no way this is not correct way to derive this formula, but this is kind of give you an idea why we have this expression for potential energy of the system, two particles. This slide is just a quick review what I just told you. Electric potential energy is given by this formula K q1 q2 r. If you want to go fancy, instead of K we can always use 1 over 4 pi epsilon naught, but otherwise it is the same formula, just different way to represent the constant of proportionality. And most important to note is that electric potential energy varies as 1 over r, while force varies as 1 over r squared. And here is again repeat of two plots. So you have force between like charges and over here, and unlike charges over here. One is positive, another negative. As further away we are from a 0 point, the smaller the force is. Obviously, the further away two particles are, the smaller the force is between them. The same as for potential energy. If two charged particles close to each other and have the same sign, that's where you're going to find electric potential energy. If they are really far away, it's going to be a very small value, get smaller. And if unlike charges, we just have a negative value for potential energy. This is a little summary of what's happening. Just again review. If R becomes infinitely large, then potential energy approaches zero, and as well as electric force will also approach zero in this limit. But the same as in gravitational potential energy, what's mostly important from physics standpoint is change. And to find change, we just have to use this formula. K stays constant, multiply value of two charges, and then divide by final distance between charges, and this one is initial distance between charges. You can kind of simplify this formula this way, just to see what's happening. K, Q1, Q2, we can factor out, and over here you have difference between final distance, 1 over initial distance. So that's what it is. What's going to happen if we have more charges than just 2-point charges, say 3, 4? What's happening with electric potential energy? It's the same superposition principle as always, and we just have to find, look at it one at a time and do a counting. So results of the 2-point charges can be extended by using the superposition principle. We're going to solve example problems like that. If there's a collection of point charges, the total potential energy is the sum of potential energy of each pair of charges. So let's say you have 1, 2, 3. So first you'll look at combination 1, 2, then combination 2, 3, then combination 1, 3, and then you add them all up. And what do we do if we're given complex charge distribution? Well, in a similar way, we can always try to treat it as collection of point charges and arrange it in some particular manner to simplify the problem. So this is the end of this video. The next video we'll be solving problems.